Hello everyone, this is Group 161 and our project is credit card fraud detection using deep learning. Fraudulent transactions pose a significant risk to both consumers and financial institutions, leading to substantial financial losses. Traditional detection systems often fall short due to their reliance on static rules that cannot adapt to new fraud tactics. This project aims to create a dynamic AI-driven solution that not only identifies fraudulent transactions in real time, but also minimizes the inconvenience to legitimate users. The dataset we are using consists of 28 anonymized features, which are crucial for maintaining user privacy while still providing valuable insights for fraud detection. By employing principal component analysis, we can effectively reduce dimensionality and focus on the most relevant features. The model's ability to predict fraudulent transaction hinges on these inputs, particularly the transaction amount and timing, which can reveal unusual patterns. Our goal is to ensure that the model is sensitive enough to detect fraud without overwhelming users with false alarms. To achieve optimal performance in fraud detection, we will implement a variety of models, starting with traditional machine learning algorithms as baselines. These models include logistic regression and random forest. Will provide a foundation for comparison. Additionally, we will explore deep learning architectures, specifically multi-layer perceptron and long short-term memory networks, which are designed to capture complex patterns and sequential dependencies in transaction data. This comprehensive approach will help us identify the most effective model for real-time detection. Given the rarity of fraud cases, relying solely on accuracy as a performance metric is insufficient. Instead, we will focus on metrics such as precision recall curve and FN score, which provide a more nuanced understanding of model performance in the context of class imbalance. The ROC-AUC score will help us evaluate the model's ability to distinguish between legitimate and fraudulent transactions. In this project, we developed two deep learning models, a multi-layer perceptron and a long short-term memory network. MLP uses fully connected dense layers, which are ideal for structured tabular data like our transaction features. It allows the model to learn complex patterns through multiple hidden layers. LSTM is designed for sequential data, and while our data isn't inherently time series, we reshaped it to treat each transaction as a short sequence of features to test if capturing feature dependencies could boost performance. We used fivefold cross-validation to ensure our models generalized well and weren't overfitting to any particular split of the data. This technique helps simulate real-world variability in fraud patterns. To prevent overfitting during training, we also used early stopping, which halts training if the validation loss doesn't improve for 3 consecutive epochs. All models were optimized using binary cross-entropy loss and the Adam optimizer, and we added dropout regularization between layers to ensure the models remain robust and avoid learning noise in the data. Here we present the performance of the MLP model. First, to explain the architecture, we used a sequential model starting with an input layer connected to a dense layer with 64 neurons and ReLU activation, followed by dropout. Then another dense layer with 32 neurons and another dropout layer. Finally, we have a single output neuron with a sigmoid function, which gives us a probability for fraud. The model was compiled with binary cross entropy as the loss function and trained using the Adam optimizer. We used early stopping with a patience of 3 and a validation split of 20% during training. The results were very strong. F1 score 0.999, ROC-AUC 0.999. This indicates that the model was highly successful in identifying fraud while maintaining very low false positives and false negatives. In fraud detection, this level of performance is critical because even few false positives can cause customer dissatisfaction and distrust in the system. The MLP's consistency and speed make it a viable option for real-world fraud detection pipelines. Moving on to the LSTM model. This model was chosen to explore whether sequential modeling across the input features could uncover deeper patterns. To use an LSTM, we reshaped our input data into 3D. Each transaction becomes a sequence of one time step with 30 features. The architecture started with an LSTM layer with 64 units, followed by dropout, then a dense layer with 32 neurons, and another dropout layer ending with a sigmoid activated output neuron. The training process was the same as MLP. Binary cross entropy loss, Adam optimizer, early stopping, 20% validation speed. LSTM achieved F1 score of 0.999, high precision and recall, and ROC AUC of 0.999. It performed slightly better than MLP in terms of reducing false positives, which is especially valuable in fraud detection. Importantly, the model showed minimal overfitting thanks to our regularization strategy and validation process. This confirms that even when using limited sequential data, LSTM is capable of extracting richer feature interactions compared to purely feed-forward models like MLP. When comparing the performance of deep learning models to baseline models, it is evident that MLP and LSTM significantly outperform traditional approaches in terms of F1 score, precision, and ROC-AVC. This comparison highlights the importance of adopting advanced techniques to address the challenges posed by rare fraud cases. The expertise of our team member in detecting fraudulent transactions using machine learning has been invaluable to this project. The references include recent studies and datasets from reputable sources like Kaggle, which are essential for validating our approach and ensuring that we are building on established research. Thank you for your time.